Hello everyone and welcome to today's lecture. Today I'd like to start off by answering a question, which is the main question dealing with what we'll be talking about in this course, and that is, what is a mathematical model? And this is going to be the main thing that we'll be studying in this course. So before we get started, we want to kind of have a good idea of exactly what a model is and what it constitutes. And I guess I should start off by saying that this is a loaded question with many possible definitions. We make mathematical models daily, without even thinking about it or without paying attention. And to give you a good example of this, think about one of the most basic questions that you might ask yourself. It's, how do I get downtown, or how do I get to a place? And there's many factors that you might consider, and you might not even realize that you're considering and weighing these factors against one another. But for one, and the distance of where you're going is one of the factors that is going to factor into this decision. The money that you want to pay to get there, whether you want to take the bus or ride a bike or drive a car. And this brings up another very important factor, which is time, or traversal time. How long do you want to take on the trip? Do you want to walk? Take a very long time. But if it's a short distance, you can walk in no time at all. Another consideration that you might make is security. How do you want to get there? Are you bringing money with you? Are you carrying money on you, or anything valuable on you? And then this also brings up, all these are kind of related to one another, but the means of transportation. So are you taking the bus? Are you going to order an Uber? Are you going to bike? Another factor is your mood. Are you rushing? It's kind of related to time and distance. Are you rushing to get somewhere? Are you having a kind of a leisurely stroll? But there are many other examples, and there are also, in this example, many other factors that you might want to consider. But here's one simple example of how we create a mathematical model, all the time when we're solving problems without even realizing it sometimes. So to put a definition down to mathematical modeling is not necessarily the easiest goal, but again, like I said, I'll try to describe it. And a lot of the examples and the material, specifically this definition that I'm about to write down, comes from a very, very, very good textbook from one of my advisors, Meyer Humi, and this is the textbook Introduction to Mathematical Modeling. And if you're going to get any companion textbook for this course, I would recommend this textbook in addition to the others that I've provided in the syllabus, because this is a fantastic overview and in-depth look at many of the modern aspects to mathematical modeling. but right now I'll write down the definition to mathematical modeling given in his book. In general, modeling is the art of describing in symbolic language this is where your mathematical and physics theories come in. A real-life system so that approximately correct predictions can be made regarding the behavior or the evolution of the system. And there are a number of different takeaways here that we want to make from this definition. The main ones being that modeling is an art. And what that means is that there are no rigid rules. Outside of the confines of the mathematical theory and we could also say physical theory here as well. That you are using. To describe the system. And this is a very, very important point. It really is an art, and it's an art that you develop over time. So you become better and better at it over time, and with time and practice. And I also want to point out that, so however here, there are patterns these are patterns of best practice that are common to good mathematical models, or to just good models. and these help avoid many pitfalls that are common to creating a mathematical model. The other takeaway that I want to give you and that I want to point out about this definition is that correct predictions usually does not mean 100% accuracy. All mathematical models have limitations, and as such, it's up as us to the creators of the models, or those creating the models, to clearly state and investigate these limitations. And I should also put the user here as well, because many times you can use a mathematical model and not be the creator of the mathematical model. But regardless, if you're using a mathematical model or you create one, you have to determine the limitations and clearly state the limitations. The other thing that I want to point out when it comes to this correct predictions is that sometimes several models describe the same phenomena, with varying degrees of accuracy, and complexity. Sometimes a model that is too complex may be a more accurate description of reality, but be very, very hard to apply. And a simpler model will actually describe the real life phenomena in a much an accurate enough way, and it'll be good enough. And what I want to do is give you a very, very, very good example of this. Just one example of this, and this is the example of gravitation theory, the theory of gravity. And there are two main theories of gravity. There are many theories of gravity that have been developed, but the two main theories of gravity that have been developed by physical scientists and by humanity are the Newtonian theory of gravity, or Newton's theory of gravity, and that of Einstein's theory of general relativity, Albert Einstein. And I'll also include, because I include special relativity over here, I'll include Newton's theory of mechanics and gravitation. So we'll start out by comparing and contrasting these two major developments in scientific understanding of mechanics and gravitation. Newton developed his theory around 1687, and there is some controversy between whether he discovered parts of the theory and others discovered parts of the theory, like Robert Hooke. But we'll avoid that controversy for now by just saying it's Newton's theory of gravity, and start out by saying this is an extremely successful theory of mechanics and gravitation. Is so successful, in fact, that this theory was actually used to achieve the moon landing in the Apollo missions, which is one of the biggest achievements of mankind. It's also used by current day astronomers and astronauts in current day missions where relativistic corrections are not needed. We can use Newton's theory of gravitation to actually mathematically prove, Kepler's 3 laws. And this is something I do in my graduate engineering mathematics class. So Kepler's laws, you'll remember, are 3 main laws of motion, one being that planetary orbits follow what are called conic sections, or ellipses, parabolas, or hyperbolas. They also relate the area of traversal to the period of motion, and give you a relationship between the period and the length of the semi-major axis of an orbit of a planet around a massive body. this theory is also easier to apply and use than relativity. I put this in quotation marks here because there are some caveats, but in general, it's much easier to apply. And use than Einstein's theory of relativity. However, there are, for all of the benefits of this theory, there are some major limitations. And perhaps, the most historic and biggest limitation was its failure to calculate the precession of various planets, of the perihelion of various planets. Specifically, Mercury, its prediction is way off. Another limitation is that the angular deflection of light, or light rays, around gravitational bodies is also way off. For instance, if you have the sun here, and you're on the Earth right here, light rays, as they pass through the sun, if they're coming in like this, end up getting deflected by the gravitation of the body. So, for instance, if you're looking at a star and you see a star in this direction from the Earth, the actual location of that star is over here, and this is because of the gravitation of the sun. It actually deflects light rays. This is not well predicted at all by Newton's theory of gravity. And in general, for the Newton's theory of gravitation, errors build up over time. Which means it's not good for long time spans, or for predicting over long time spans. This is a summary of Newton's theory of mechanics and gravitation. On the other hand, we have Einstein's theory of special and general relativity. Einstein published his papers around 1916, and this is also an extremely successful theory of gravitation. This is definitely a very, very, very big theory because it fundamentally changes the idea of space and time. Einstein's theory of general relativity is actually required to create modern GPS systems and a number of other modern systems. And in general, by greatly overhauling a lot of the fundamental ideas of space and time and fundamental ideas in physics, the theory addresses and explains and corrects the limitations of Newton's theory. While simultaneously better explaining why gravity works. And in general, it's much harder to correctly understand apply and solve problems. In general relativity. There are definitely some other limitations to this theory as well. Extreme scenarios such as very, very large mass like black holes, we have complications because there's a fundamental misunderstanding of how general relativity, which works at large scales for very large distances and large scales between planets, interacts well with quantum mechanics, which is the theory of the very small, so extremely small fundamental particles. So in general, Einstein's theory of relativity doesn't mesh well with quantum mechanics. and this is actually one of the biggest problems in physics right now, is to find a new physical theory that that gives us Einstein's theory of general relativity, but meshes that with quantum mechanics. But in terms of just theories of gravitation, the more modern theory, and some people would say the better theory, is Einstein's theory of special and general relativity. But I wouldn't say that it's better. I just think that it's more modern and it's more accurate. It's a more accurate theory. And significant accomplishments in mankind have been achieved by both theories. World-changing accomplishments have been attained using both these theories. What's also important to note, and this is the final note that I'll make on this example, is that sometimes if you have one theory that's less accurate, one theory that's more accurate, you can address and use the less accurate theory while introducing corrections from the more accurate theory. So for this example, Newton's law I should say Newton's theory of gravitation can often be used with, and is often used, with what are called relativistic corrections. Tacked on, or attach. Which will correct Newton's laws and add in the corrections that we know are actually true and observed in real life, that can be explained via relativity. And we'll investigate this a little bit later on in the course when we get some development into our toolbox or our technique. But the main thing you want to be thinking of in this course and in general when you're learning mathematics is how it's adding to your toolbox for mathematical modeling and for figuring out problems using mathematics. So what I want to do now is just give a quick overview of the general modeling framework and what mathematical modeling problem consists of, and how it's typically a very large process. And just like the previous definition, this process can be found in Meyer-Hume's book, and I very strongly recommend taking a look at the book because it's a very, very nice and very, very, very extremely detailed and informative summary of how to make a mathematical model, and very, very in-depth as well. The step 0 in this process is to set up as precisely as possible the reasons for constructing the model. And its objectives. So, for example, if you're making a model of the weather and you want to predict the weather, do you want to predict the weather for a day? Do you want to predict the weather for an hour? Do you want to predict the weather for a week? Right? Each one of those questions is a different question. It's they all are very difficult questions, but they have very different difficulties associated with them. And as you can see, if you look at your local weather forecasts, you don't really get much accuracy even within a few days for weather forecasts. So the next step, step 1, is to study the problem as it is in real life. And this involves doing a lot of research to figure out exactly what the problem is you're dealing with, and what exactly is going on. It's also setting up for the next step, step 2, which is data collection and analysis in real life. And this is where you go out into the field, or you collect data from laboratories, and you collect real world data to analyze. And this actually then leads into step 3, where you design controlled laboratory studies and simulations. And then the last 2 steps here are step 4 and step 5. Step 4 is the construction of a conceptual qualitative model. And notice that I'm using the word qualitative here, not quantitative. And the last step here is conclusions, making conclusions, predictions, and recommendations that follow from this qualitative model. And that's the last step of this process. these 5 steps are the form the basis of a given model, right, in science. But essentially, these steps are very often not enough. And these steps are only the beginning of the modeling process. So these 5 steps, and I've just made a box around these steps because they all together form the basis for what's called a qualitative model. And these are used very, very often, and they are useful and can be useful. But it's important to point out that while qualitative models are, they are extensively used in the social sciences. And they're also used in the physical sciences, the natural sciences, and engineering as well. But it's important to point out that they are rarely accepted as fact in the natural sciences. And by natural sciences here, we're talking about physics, chemistry, biology, etc., etc. In these fields, we have to perform additional steps. Which lead to a mathematical quantitative model. And notice my use of the word quantitative here rather than qualitative. So forming a qualitative model is very often a very useful first step and very important when constructing a given theory, a given physical theory, or a given mathematical model. But we need to do more as natural scientists, engineers, and applied mathematicians to construct real-world models. And this is where step 6 comes in. And step 6 is the step where we do abstraction and symbolic representation. And the main idea here, we have a couple different important points here in step 6. Typically, step 6 requires insight and a lot of creativity to complete. And the reason for this is that typically the true variables which control phenomena are often masked by the data. That's not to mean that we can't use the data and do many of the amazing modern data science algorithms that have come about, but typically requiring or trying to find out what the true variables are which control a certain phenomena involves a large amount of insight and creativity to come up with a correct symbolic representation and model. And this is also where this step is where a good knowledge of modern mathematics and the physical sciences is often crucial. And these are my comments on this step, but essentially it consists of representing variables by symbols, naming the functions or other mathematical relations, that relate the symbols and that are going to be used in the model, and identifying the axioms and or constraints of the model. And this step immediately jumps into then the next step, step 7, which is to derive the equations that govern the phenomena being studied. And some good questions to ask here, and are the general classifications of types of models. Is this model a stochastic model? Or probabilistic? Like, for instance, quantum mechanics is. Or is the model deterministic? This would be general relativity. So stochastic means there's some degree of randomness in the model, and you have to use probability theory very heavily in the model. Or deterministic, meaning you can always find an exact trajectory or an exact solution. Or is it a mixture of both? This can happen sometimes. Another big question to ask is the model continuous? So will you be using techniques from calculus or topology to discuss the model and solve problems, or discrete? Meaning you'll be using methods from discrete mathematics or logic. And in every case you'll be using logic. But the idea is, both continuous and discrete models have large applications and large spectrum of applicability to real-world problems. And just like before, you can say, or is it a combination of both? There are many models that require you to consider both discrete forms of the model along with continuous forms and combining them. The main idea here is that this step is where the mathematical methods used must be precise and correct. So you have to correctly apply mathematics and the mathematical theorems that you're going to use in the confines of the mathematical construct that you're using. once you have your mathematical model and you've completed steps 6 and step 7, you'll move on to step 8. Which is model testing. And this is the meat of this process, because it's the probably the most difficult and also the most rewarding part of this process. It's finding solutions to the model from step 7. And not just finding solutions, but comparing solutions to the model equations. So we compare this is where we really kind of get to test our mathematical model that we've created and see if it actually applies to reality and if it actually works. And generally speaking, solutions here mean a number of different things, but in this class, and as you might have seen if you talked about numerical methods at all in your normal ordinary differential equations class or in your linear algebra class, solutions come in two forms typically. The first form is the exact analytical solution, and the second form is a numerical solution or a computational solution. And the numerical or computational solution is typically we think of it as an approximation to the exact analytical solution. And this in and of itself is a problem in mathematical modeling, is studying a given numerical procedure or algorithm and showing that procedure, proving that procedure is correctly approximating the exact solution. This is a huge problem in mathematics. I recommend taking a numerical methods course to learn more about this. We will be going over some basic numerical methods in the course and showing how to do basic numerical methods for differential equations. However, I won't be going over them in detail in the course. We'll be focusing more on getting exact analytical solutions and investigating exact analytical solutions, even if we can't get the exact solution itself. There are many exact methods that have been developed for that. So we'll be talking about that a lot in this course. And it's at this step where if in this testing you have a bad fit, let's say you have a bad fit, to your model, means steps 4, 5, and 6 and 7 must be revisited. once you have a working model that is you're sufficiently sure that you've done step 8 here and you've tested your model, step 9 is an investigation of your model limitations and constraints in the model. So you really push it to the extreme, and you figure out what the limitations and constraints of your model are. I guess what I'll say is investigate model limitations and constraints. You really want to push your model to its limits and the boundaries of the limits to really test and figure out what the true limitations and constraints of the model are. Just like what we saw in the previous example, and all of these steps you can apply to the comparison between relativity and Newtonian mechanics. But for example, Newtonian mechanics can definitely not be used to predict motion close to the speed of light. Another good example that I'll revisit a little bit later on is the ideal gas law, which you will hopefully be familiar with from high school or from a chemistry course, if you're taking a chemistry course. Remember, this as Pivnert. P, pressure times volume of a gas, is equal to N times R, which is the constant, times the temperature of the gas, is a good model for some gases but not for others. Once you've performed this deep investigation of the model limitations and you figured out, what the boundaries of your model are in terms of its limitations, you can then move on to the next step, which is what's called predictions and sensitivity analysis. And This could consist of a lot of different things, but then the main idea here is how sensitive is the model. To small variations in parameters or terms in the model. Or we'll say variations, say, in parameters of the model. Some models are required to be more sensitive than others, and some less. And I'll give a good example of this here. We call a chaotic system a system that displays the following. And we'll investigate in this course a number of different so-called chaotic systems. When the evolution of a system displays high sensitivity to initial conditions, to its parameters, the system is said to be chaotic. And for such systems, it's only possible to make short-time predictions. Or small parameters, so short-time predictions are only possible. And this is a good example of why weather forecasts are accurate only for a few days. The chaotic nature of the system, and that all of the variables that are going together, even a basic model for weather patterns and for the weather exhibits chaos. And sometimes not at all. Sometimes you get a weather forecast, and the weather forecast is completely different than what was predicted. So it's very, very important to see this. This is a very good example of such a system, and we'll see some systems with differential equations that actually come from basic assumptions about the atmosphere. So the Lorentz equations, the Lorentz system, is a fantastic example of a chaotic system, and we'll actually investigate this numerically by the end of the course and see how we can approach this and learn from this. But so once we've established results about the sensitivity of our system, we can move on to step 11. Which consists of making extensions and refinements to the theory that we've built up from the ground. And this really consists of going back to the limitations and seeing how we can kind of update and make our theory better and more accurate to cover the things that we found that were limitations in the previous steps. So, for example, a great example of this that I told you earlier that I would mention is that the ideal gas law needs a refinement under certain scenarios, and under very common scenarios. When the gas molecules are large, for example, in diatomic gases, but there are other examples as well. And so typically this extension takes one of the following forms. Could take, say, the pressure times or plus some constant alpha over v squared is equal to times v is equal to n times r times t. Remember, the ideal gas law said was PV equals nRT. And there's actually a whole class of extensions like this called virial expansions. Of varying difficulties, but it's all in general related to extending this ideal gas law to be more realistic. You could have the pressure is equal to n times r times t over v times 1 plus bt over v, where b is a function of t, it depends on the temperature. More complicated one would be that P equals nRT over V times 1 plus MB NB T over V plus NC over V plus M n to the K U over V to the 2n to the K plus n to the 2K W over V to the 2. Okay, where B, C, U, and W are all functions of t. And there are a number of different extensions here that we could think of. But the idea here is that under varying circumstances, the ideal gas law is not enough, and it's not accurate at all. These extensions are more accurate and are in a refinement of our original theory. And so once we've done this, or we think we've successfully done this, extended our theory and refined our theory enough, we can do what's called compounding. And this is the last step of this process. So once we've refined and extended our theory as far as we need it, or as far as it can go, so once we have a reliable model that we found that we're okay with, we can model related, more complex problems by compounding, and that's really what compounding is. It's kind of taking our model and building it up and applying it to larger and larger systems. So for example, one of the things that we'll talk about a lot in this course are both linear and nonlinear springs. But let's just say, if you've taken a course in ordinary differential equations or physics, you're familiar with a spring mass system. So compounding would be, steps 1 through 11. Let's say we go through and we develop a suitable model for a spring mass system. This describes the motion of a mass M and spring of stiffness K and its motion about its equilibrium point. Back and forth, back and forth, back and forth. So once we have this successful model, which you should hopefully be familiar with, we can then compound it. By considering the motion of a number of different springs and masses that are connected to one another. The motion of which will be much more complicated. We'll say K1, M1, K2, M2, K3, M3, K4, M4, K5, M5, K6, M6, and so on and so forth. You can continue this. And this model can then be compounded even further and used to study one-dimensional longitudinal wave propagation. Along an elastic bar. take this picture right here, this picture, and consider, we continue going with it indefinitely. Spring mass, spring mass, spring mass, spring mass, and we shrink it. Oops, don't want to shrink it just yet. So make it very, very, very small. And this is going to keep going, keep going, keep going all the way along. So. And I'll get rid of these as well. And so in the limit, as this system goes smaller and smaller and smaller and smaller, this is identical to what's called one-dimensional wave propagation along in a longitudinal elastic bar. So we can show very, very clearly and concisely that the phenomena that's being modeled by this spring mass system is the same phenomena as if you have an elastic bar, a continuous elastic bar, and you study the disturbances that propagate through this elastic bar. So you can say have an elastic disturbance because you hit one end of the bar, and you want to study how this disturbance or how this wave travels through the bar. That's called longitudinal P wave. We have a P wave moving like this and a P wave moving like that. But the idea is that by compounding the spring mass model, we can jump up even further to actually go from a system. So we'll see that this is a single ordinary differential equation for the motion of this mass. This model consists of a system of ordinary differential equations that govern the motion of all of these masses, and then in the limit, we actually get a partial differential equation called the wave equation that governs wave disturbances moving along this bar. This is a great example of compounding a problem. And if you're wondering what a longitudinal wave looks like, I have a little animation that I can show you. So this is what a P wave would look like, or a longitudinal P wave would look like as it travels through the material. And this is exactly the behavior that you would expect from systems of springs and masses. If you say jostle one end, this disturbance will move through it. So this finishes this 12-step process. Essentially, gives us all of a great summary of everything we need to know about mathematical modeling. It may at first seem a little bit overwhelming. Steps 1 through 5 is a qualitative model. And in this course, we'll be really focusing on steps 6 through 12, which is more computing a quantitative model or finding a quantitative model of a phenomenon. And again, I can't recommend Meyer-Hume's book enough. So much so that there's a great kind of like summary in this chapter that I'll now include in these notes. And this is again from Meyer-Hume's book. Intro to Mathematical Modeling. But this is just a very, very nice spreadsheet showing us exactly, or a very nice diagram showing us exactly what constitutes a mathematical model, with steps 1 through 5 being this upper triangle right here, and the steps that we'll be focusing on in the course being the lower half of this triangle right here. And it really shows you how the modeling process is essentially a feedback loop, where if you're doing it correctly, you should be kind of going around each one of these multiple times and refining your model, making predictions and conclusions, validating your model, and so on and so forth. But we'll really be focusing on the mathematics. And I hope everyone has a great day.